Hello everybody. In this video, we are going to talk about what is a combinational circuit and how to design it. To understand it further, we solve a problem 4.4 which has two sections A and B from Digital Design by Moris Mano's 5th edition. Okay, let's get started. First, let's see about the block diagram of the combinational circuit. The block diagram consists of a black box. Black box is a one which hides the inner parts or inner details from the viewers, which means the macro level working only is known when viewed from outside, but it gives the same perspective in the micro level when assumed to be opened and seen inside. Now let's move on to the definition. It is a digital circuit which is built using logic gates or combination of logic gates. It accepts binary inputs. There may be n number of inputs. Outputs at any time is a function of the inputs at that time. Output can be expressed as a Boolean function. With this, we'll see how to design or construct a combinational circuit. Here we'll see the design steps one by one. In total, it has 5 steps. The first step is the problem statement. The second step is to determine the inputs and outputs. The third step is to form a truth table. And the fourth step is to write the Boolean expression and to simplify that expression. Fifth one is to implement the circuit. And usually the word construct is not used here. We are asked to design the combinational circuit only. In order to have the clear understanding of the design of combinational circuit, we'll see one problem, that is 4.4 from Digital Design by Moris Mano's 5th edition. The problem is to design a combinational circuit with 3 inputs and 1 output. In this problem, the output is 1 when the binary value of the inputs is less than 3. The output is 0 otherwise. So this is the problem statement. And we have the design steps. First is to understand the problem statement. And we have to name the inputs and the outputs. Here we can name it as X, Y, Z, and we have the 3 inputs and we can take F1 as the output. And the next one is to form the truth table. Before going to form a truth table, you should know the definition of a truth table or what is a truth table. The truth table is the table that shows all the possible combinations of inputs and then corresponding outputs. So in this truth table, you should know how many rows you should have and how many columns you should have. Since we have 3 number of inputs, we can take it as 2 power 3, that is 8 number of rows. And the columns must be 4 because we have 3 inputs and 1 output. If needed, one extra binary value can be added as a column. Write all 8 possible input combinations in binary and fill up that output column with ones or zeros depending on the problem statement. Then we write the Boolean expression for the output. If needed, we are going to simplify it using Boolean laws or using K-map. And then we'll implement the circuit corresponding to the output expression. Okay, now we'll see each and everything in minute detail. Okay, so the first step is the problem statement. It is to design a combinational circuit. From that, we understand that it is a combinational circuit and that should have only inputs and outputs. There is no feedback path. And it produces a 1. That indicates that we have the output equal to 1 when its 3 bits binary values less than 3. That means here we have the combination of this inputs, right? So if the input value is less than 3, then you get an output as 1. Otherwise it is 0. Now we go for the design step 2. It is to determine the inputs and outputs. So we determine this X, Y, Z as inputs and F1 as output. Then the design step 3. It is to form the truth table. And we should know the required number of columns, required number of rows. So we have 3 inputs and 1 output as the column. So we need to have 4 columns and the number of rows is equal to 8. That is 2 power number of inputs. We have 3 inputs, so it is 8. Then we have to fill up all these input combinations and corresponding output column with the ones or zeros depending on the problem statement. So now we are going to have this truth table. So we have written all this input combination from 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, then 1, 0, 0, 1, 0, 1, 1, 1, 0 to 1, 1, 1. So from 0 to 7, we have written the combinations in binary. Okay. Here this X, Y, Z are inputs and F1 is the output. In order to know that when its 3 bits binary values less than 3, we have marked this binary values starting from 0 to 7 for this combination. So when it is less than 3 means for this value 0, 1 and 2, we place 1s for this F1 column. Okay. Otherwise, we place zeros for the rest of the rows. So for the binary values less than 3, that means 0, 1, 2, we place 1s corresponding to this F1 and the remaining rows will be filled with zeros. Okay. So we have formed this truth table now. Now we move on to design step 4. So it is to write the Boolean expression for the output F1. Then we need to simplify it using K-map and Boolean laws. So what is the Boolean expression for this? So for this one, we have to write the expression. We know that it corresponds to this 0, 0, 0. That means this is X dash, this is Y dash, this is Z dash. Okay. Then we move on to the next. Here also we have a 1. So corresponding to that, we can write the expression as this X dash, Y dash and then Z. That means 0 represents complement value and 1 represents its original value. Then we move on to the third output value, that is corresponding to the 0, 1, 0. So we get it as X dash, Y, Z dash. So with this we get this output F1 as X dash, Y dash, Z dash plus X dash, Y dash, Z plus X dash, Y, Z dash. Now this expression is available in SOP form, sum of product. Now we want to simplify it. Okay, for that we need to have a K-map first. Since we have only 3 variables, we have a 3 variable K-map here. So we marked all these details like X, Y, Z here and here it is X dash X. And then on this 4 columns we have written it as Y dash Z dash, Y dash Z, Y Z and Y Z dash. Corresponding to each and every cell we mark the midterm values as 0, 1. Then here it is 3, 2, then 4, 5, 7, 6. Now for the available output expression, we have to place a 1s here. So for this X dash, Y dash, Z dash, that represents a 1 into the 0th cell. Because we know that it is X dash here, then Y dash is Z dash. Then corresponding to this X dash, Y dash is Z, isn't it? So it is X dash, Y dash is Z. Corresponding to this first cell, we have to place a 1. Then corresponding to the third term, that is X dash, Y Z dash. So here it is X dash, Y Z dash means that corresponds to the second cell, we place a 1. Now we are going to group them. So we can group it like this. So this is our first loop and its expression is X dash, Y dash. How do we get it? Here we have this X dash. On this column wise, we have this Y dash, Z dash and Y dash is Z. So this Y dash is redundant, so we can take it once here, and this Z dash and Z or complement of each other, they can be cancelled. So we got this X dash, Y dash. Then we are going to have this 1 that to be grouped along with the 0th cell. Okay, so this 0th cell and second cell are combined, so that we get the expression here as this X dash along with this Y dash, Z dash and Y Z dash. And this Y dash and Y get cancelled because of this complement. Okay, then we get the answer as X dash Z dash. So the simplified expression is F1 is equal to X dash Y dash plus X dash Z dash. That can be written as F1 simplified. And using Boolean law, we can take this X dash outside, so that you will get it as X dash into Y dash plus Z dash. So we are now moving on to design step number 5. In this, we have to draw the circuit diagram. That means it is also known as implementation. So for this, we draw three input lines that corresponds to this x dash, y dash and z dash. After that, we want to combine this y dash and z dash using this plus operator that represents this OR operation, isn't it? So we need a OR gate. So using OR gate, we combine this y dash and z dash. So this operation is over. After that, that y dash plus z dash within this bracket, that should be combined along with this dot product, okay, with the x dash. So this result must be combined with this x dash using AND operator, so that we'll get this F1, that is F1 simplified. Okay, so we got the combinational circuit designed by us. So the first part is over. Now we move on to the second part. So what is the second part? The output is 1 when the binary value of the inputs is an even number. Okay, so I am not going into much detail. Now we start from this truth table because we know the problem statement. So in this truth table, we have written all the input combinations. That means 8 possible combinations are written. And what is given in this problem? The output is 1 when the binary value of the input is an even number. Okay, so we add this binary values. So 0 is even number, then 2 is an even number, 4 is an even number, 6 is an even number. So for that even numbers, we place 1. Okay, 0, 2, 4 and then 6. The rest of the values will be 0 here. Okay. Now we write the Boolean expression corresponding to this. So for this one, it is x dash, y dash, z dash, isn't it? Then for this one, it corresponds to 0, 1, 0. So we write the term as x dash, y, z dash. Then corresponding to this one, we have the input combination as 1, 0, 0. That means it is x, y dash, z dash. Then corresponding to this one, we have the input combination as 1, 1, 0. That means it is x, y and z dash. Okay. Now we write the Boolean expression as f2 equals x dash, y dash, z dash plus x dash, y, z dash plus x, y dash, z dash plus x, y, z dash. That means these four terms are combined using plus terms. That is, it is sum of product, SOP form. Now we are going to simplify this Boolean expression using K-map. So in this expression, we have these four terms. They will be represented as ones into this K-map. So here first we have this x dash, y dash, z dash. So that corresponds to the 0th cell. So in that we place a 1. Then here we have x dash, y, z dash. So this is 2, right? X dash, y, z dash. To this cell we place a 1. Then the next term is x, y dash, z dash. So that corresponds to x, y dash, z dash. That corresponds to this 4th cell. So we place a 1. Then next corresponds to this x, y, z dash. That means this x, y, z dash. That corresponds to the 6th cell. So we place a 1 into the cell. Now the next step in this one is to combine the ones. So here these 4 ones can be combined as a quad and it makes a group, and the corresponding expression for this one is z dash, because here on this side these 2 rows are covered by this group. So x dash, x cancelled out. Then here on this column wise we get this y dash, z dash and this y z dash. That means this y dash and y are complement of each other, they can be cancelled, and here this z dash only exists. So the answer is z dash. So F2 simplified is z dash. Now the next step is to draw the circuit diagram, or we have to give the implementation. So what is it? It is for the output expression F2 simplified is equal to z dash. So now we draw the input line corresponds to this x, y and z, and this z dash is required. So we connect a NOT gate or an inverter and the output is taken. Okay, so we get this z dash. So this is how we design a circuit. You may ask me why we have put this as x, y, z in the second section, while in the first section we have the inputs as x dash, y dash, z dash. The inputs will be available in primed as unprimed format. Okay, that means original as well as the complement form. So it is better to use the desired ones or needed ones as such. Okay, so here we have needed this x dash y dash z dash, so we have taken the connection from these primed values. But in this case we don't need this x and y, only z is needed. So we can take the connection from this Z and then it can be applied to your inverter and then you can get the output. Otherwise, if needed, you can also do it, or you can also take the connection out of this Z dash input and get it as an output. Okay, so we have done with this combinational circuit definition and the explanation, and we have seen two examples also. Okay, hope you have understood. Hope